The accurate estimation of the two-phase pressure drop plays a major role in the simulation of thermohydraulic systems, especially during transient events. The pressure drop does not only affect the stability's limits of the two-phase flow instabilities phenomena but also determines the initiation of abnormal heat transfer mechanisms. However, existing two-phase flow pressure drop laws suffers of large uncertainties and limited prediction capabilities. From a fundamental point of view, a long-lasting question has been if physical similarity does exist in the case of the two-phase flow pressure drop, and if exists, which are the transformations requires to achieve similarity. To answer these questions, the Thermal Two-Phase Flow Lab initiated an experimental study for obtaining pressure drop measurements in a large range of conditions. First, experiments with different mass fluxes and with the same working pressure were selected. In this way, all the thermodynamic properties are kept constant. The curves are showing a similar trend by they are not overlapping. However, if the two-phase pressure drop is scaled in terms of the all-liquid pressure drop as suggested by Bolter and Kepner in 1939, all the curves collapse into one curve. To reduce uncertainties, the all-liquid pressure drop was measured for each case instead of being estimated from correlations. The curves show similarity for the same working pressure. Even when the changes in the mass flux have a strong influence on the flow patterns, no noticeable effect on the pressure drop is observed. This agrees with the observation from Martinelli in 1944. Second experiment, the working pressure was varied while the mass flux was kept constant. Changes in the thermodynamic properties break down the similarity. So now, the main question is which mechanism causes the breakdown of the similarity, and if there exists a transformation that can recover it. It is possible to hypothesize that the breakdown of the similarity is caused by the changes in the flow patterns, and thus influenced by the surface tension, or by irreversible pressure drop losses at the liquid-vapor interface and thus influenced by the liquid and vapor viscosities, or by changes in the flow velocity caused by the changes in the liquid and vapor densities. The effect of the flow regimes on the pressure drop was already ruled out by Martinelli in 1944. If irreversible pressure drop losses at the liquid-vapor interface are dominant, then the flow regimes must have a strong influence on the pressure drop, and they don't. Then, the breakdown on the similarity might be caused by changes of the velocity due to the changes in the liquid and vapor densities. However, as the density ratio cannot be the scaling parameter, then the liquid and vapor density difference, and the vapor density must be the governing parameters. The result was surprising, as this dimensionless group was not considered before as the only dominant governing parameter. An exception was the work of Owens in 1961. Now, it is possible to recover the similarity up to qualities of 0.6. At higher qualities, the similarity breaks down again and a different approach is required for recovering the similarity.